The Royal Swedish Academy of Sciences has today decided to award the 2025 Nobel Prize in Physics to...
This was the Nobel Prize announcement this Tuesday for physics in 2025. They received the Nobel Prize for something extraordinary, namely that the quantum phenomena that we see in subatomic particles like electrons, protons, and so on also appear in the case of objects we can see with the naked eye, macroscopic objects. And here we're talking about the phenomenon of quantum tunneling, the ability of subatomic particles to pass through walls, or are we talking about the discretization of energy levels? Well, they showed that these phenomena take place in superconductors, and superconductors are large enough that we can see them with the naked eye. Their research was inspired by Nobel Prize winner Professor Antony Leguet in 2003, and who, by the way, was part of the evaluation committee for my PhD thesis. Over time, this research led to the emergence of quantum computers, especially qubits, which are the memory elements of quantum computers. Keep in mind, these are semiconductor-based qubits because there are other types of qubits as well. Well, I'm going to speak freely in this video, especially since it also has a personal touch through Professor Leguet, whom I worked with. I'm going to give you the list here, and I'm afraid it's going to take a while again because I'll probably talk a lot. There are 10 points, and you realize if I talk for 3 minutes about each point, that's already 30 minutes. But let me tell you the points and encourage you to stay with me until the end, because personally I find it a very interesting story, especially since I went through it myself. Yes, so we're going to talk about subconductors, we're going to talk about the theory of superconductors, meaning to understand the essence, sir. What's happening there, right? After that, we'll talk about Josephson junctions, meaning what makes these special superconductors. Why are they later used in the qubits of quantum computers? And we'll also go through some equations, just a bit through the equations, especially since there will be some equations, similar to the inductor-capacitor circuit that we also saw in high school. Yes, inductor-capacitor electric circuit, of course, coil capacitor. And after that, we'll talk about experiments. Yes, so the experiments they did, which are about quantum tunneling, and we'll finish with qubits. I mean, why are these superconductors that have these Josephson junctions so useful for building superconducting-based qubits? And by the way, in my opinion, this technology is the most suitable for actually bringing quantum computers to the market. But for that, we need to go a bit into the details, look at the equations, see how the quantization of the energy levels happens, and discover a small, big secret there, right? And let's come out of here richer, because my dear friends, we may not be as many as on other channels, but there are some really cool things here. I think, and look, Adesor, at the comments, Adesor knows more than I do. Let's begin. The history of superconductors begins in 1908, when the Dutch physicist Amélie Onnes in the Netherlands managed to liquefy helium. Helium is a gas. He managed to turn it into a liquid and bring it to a temperature of almost 4 Kelvin. Well, guess what? After a few years, when he cooled mercury to that temperature, he saw that electric current passed through mercury without resistance, without any kind of resistance. He called this effect superconductivity. It was a mystery until 1957, when American physicists Bardeen, Cooper, and Schrieffer proposed a theory. That's very good and effective. They also got the new prize. They first thought about what happens to electrons when they travel through ordinary conductors. Why does it lose energy? Why does the conductor heat up? Because we know this from heaters. Electric current passes through a wire, let's say through a conductor, and if that conductor is very thin, at that moment the conductor heats up a lot from the passage of the current. Well, if the current passes through a superconductor, sir, it doesn't heat up at all. That means the electrons there don't lose any energy. My explanation is similar to what my professor Dirk van der Meer told me during my PhD. And he used to tell us this. Electrons in a conductor are roughly like, let's say, runners. A lot of runners going through a forest. That is, these runners are running in a group. And at some point, some of them stumble over a tree, bump into a tree, or stop in front of a tree. And in this way, they lose energy. In the same way, electrons in conductive materials behave. That is, as they move, they bump into atoms and lose energy. And what happens with superconductors, Danson was telling us? Imagine that this forest has trees arranged in an orderly way. Why? Because in crystals, in crystalline structures, just like in regular conductors, the atoms are arranged in an orderly way. Let's start over with the forest and picture the trees arranged neatly. And this time, instead of runners, we'll have dancers who dance in pairs and dance in sync. And imagine how those pairs are all dancing in sync, a very, very beautiful dance. And they move smoothly through that whole forest of orderly trees. Because their movement is synchronized and organized in such a way that all the trees can harvest it. And in this way, they move and dance beautifully, without losing any energy, without bumping into the trees. The Bardian-Cooper-Schrieffer theory, which explains superconductors, is named after the other three physicists. Yes, it basically has the same explanation. It says this: we take a conducting material and cool it to a very low temperature, just like Kamerlingh did. Once we cool it to a very low temperature. The atoms are precisely ordered in the lattice we discussed earlier. Well, the electrons also organize themselves into pairs, which are called Cooper pairs, named after one of the physicists. They organize themselves into pairs. Now they move through the conductor, synchronized with each other, and in this way they avoid the surrounding atomic structures and can move through the conductor without any loss of energy. There are online videos explaining this process, and I'll show you one here. In this case, what we see on the right is an electron in a certain location, and through electrical interactions, yes, it causes the atoms to arrange themselves toward it. So basically, it deforms the crystal structure. At that moment, an additional positive charge is created, which attracts an electron from a distance. And in this way, the two electrons form the Cooper pair. In physics, we say that the interaction between the two electrons takes place through the crystal lattice, or more precisely, through phonons, which are the quantized vibrations of the crystal lattice. It must be said that this picture is oversimplified. Why? Because the two electrons that form the Cooper pair are not localized in space. They don't stay next to each other. They are, in fact, pairs. In momentum space, what is momentum space? That would be a very long discussion, but in condensed matter physics, it's used very often. It's another representation of electrons. Instead of saying the electron is on the left or on the right, we draw a momentum space. The electron's momentum has a specific direction and magnitude. Momentum also refers to velocity. And so we arrange the electrons not by the positions they're in, but by the velocities they have, and in momentum space. A Cooper pair is made up of two electrons that have opposite momenta. So basically, the same values, but different directions, and, pay attention, opposite spins. And this is very important. The fact that they have opposite spins, yes, because together they form a particle, or rather, a quasi-particle with spin 0. That means it is a boson. Well, and from here begins the quantitative description of superconducting materials. We no longer talk about electrons as independent particles, but we always talk about pairs. Cooper, which has a double charge, right? And again, we make another analogy with ordinary particles. Let's revisit ordinary electrons, which quantum mechanics describes as a probability wave. Yes, which has an amplitude and a phase. Well, Cooper pairs are also described by probability waves, and the most important thing about these Cooper pairs is their phase. Why is the phase important? Because normally these conductors are at room temperature, they're not cooled down, so the pairs don't form at room temperature. Since the material isn't a superconductor, it must be cooled. For example, like Cameron Ligonis did at 4 Kelvin, and then it becomes a regular superconductor. Well, and in this cooling process, each material has its own temperature at which it becomes a superconductor. And at this temperature, that special process takes place through which the conductor becomes a superconductor. And this special process has to do with Cooper pairs, because when Cooper pairs form, each will have a probability wave. Yes, and the phases of all these probability waves of all the Cooper pairs align. I often imagine that they align just like the phases of photons align. Yes, light particles from a laser are photons, which are quantum particles with a probability wave and phase. Well, the difference between regular light and laser light is that the phases of these photons are all aligned. Or, well, another model if you want, yes. A platoon of soldiers all marching like this randomly when it's very hot, and then suddenly it gets very cold. And the captain or the lieutenant gives an order, yes, and everyone marches in phase, synchronized. And this is very important for our superconductivity process, because now all the pairs will have a phase. And this phase becomes a macroscopic property of the entire superconductor. With this phase, in fact, we will work from now on, and this phase will describe the properties of the superconductor and, of course, how it evolves over time. You'll see this in the equations later. Are you still with me? Or did you hear the word equation, and that's when you left goodbye? Attention, we are on our way to understand qubits, which are the essence of quantum computers. To explain qubits, we first need to discuss Josephson junctions. I'll now share some information about them. And he had a quirky idea. He said, let's take a superconducting ring and cut it on one side. We cut it a lot, so that the distance between the two ends is very large. Actually, the distance between the two ends needs to be quite small, on the order of nanometers. Yes, and to put an insulator in that area so that normally electrons can't travel from one side to the other. What have we created here? We've created a potential barrier. So if that ring is not a superconductor, yes. So if that ring is at very high temperatures, so that it's a normal conductor, the electric current wouldn't flow. Since it's an insulating area, the electron can't pass through the potential barrier electrically. And the man studied the ring with it when it cools down to become a superconductor. And guess what? A great wonder. He demonstrated that the electric current will pass through that potential barrier, so it will go through that area. Insulators, well, even more, because that ring... With the insulator, it itself generates an electric current which stays there for an infinite amount of time. So, pay attention, no electric current is applied from outside, no electric voltage is applied from anywhere. Simply put, that ring self-generates an electric current which then circulates through the ring. Yes, and it lives on forever. The properties of this electric current, its strength, and the fact that it's direct current, which I forgot to mention. These properties are determined, of course, by the nature of the superconductor, by temperature, by the normal resistance of the superconductor, by how large that junction is, because this threshold between the two where we cut, yes, is called the Josephson junction, yes, so by how large that junction is and by these parameters. But it produces an electric current that stays by itself and keeps circulating there infinitely in that ring. Well, and what do we have here? Well, first of all, we have a quantum tunneling effect, because at room temperature, yes. The electrons couldn't cross that junction in Josephson since it was an insulator, so the current and electrons wouldn't have passed. Now we have quantum tunneling, where electrons cross to the other side due to quantum effects. What are quantum effects? Who is responsible for this? Of course, the Cooper pairs I mentioned earlier. Well, and Josephson also showed mathematically how this happens. Namely, we saw that in such a superconductor condensate, where we have a lot of Cooper pairs that are all aligned, all the Cooper pairs have the same phase. Right. This condensate is described by a macroscopic quantity, which is the phase of that condensate. The condensate phase in a superconductor is usually uniform across the material. However, when an electric current flows through the superconductor or a magnetic field is applied, this phase begins to vary along the conductor. This property has fascinating consequences. In a closed superconducting ring circuit with a single Josephson junction, as I said, an electric current can appear even in the absence of an external source. Why? Because both necessary conditions are met at the same time. The phase varies along the superconductor, and the phase difference at the ends of the junction allows quantum tunneling. What does the current represent here? It is the movement of Cooper pairs crossing the junction, a quantum tunneling process between the two regions of the superconductor. And to solve these equations, we're interested in what the Josephson junction equations are. Just like we have equations for a capacitor, equations for an inductor, what, sir, are the equations for the Josephson junction? And we've seen that the most important parameter there is this macroscopic phase phi, and here you can see the equations. And if we look at the Josephson junction equations, we basically see that there are two equations. The first one connects the electric current with the phase difference phi between the two condensates at the ends of the insulator, the ends of the junction, and the second one connects the electric voltage at the terminals of the Josephson junction with the same phase difference phi. And these are two equations that are extremely strange. For example, if we take zero voltage, we solve the case of zero voltage on the Josephson junction. We see that if we substitute it into the other equation, we get a constant current. In other words, we get what I said at the beginning. If we have a superconducting ring and we have a Josephson junction, the voltage is zero because we haven't applied anything here, no kind of voltage. And yet, the current will be non-zero. So current will flow through the superconducting ring that has a Josephson junction. And if we take a direct electric voltage, in other words, if we apply a direct electric voltage to the terminals of the Josephson junction, we get an alternating current. And this is the second effect that bears Josephson's name. But what interests us is the relationship between voltage and current, because the relationship between voltage and current determines the equations of any electric circuit, just as we have for the capacitor and for the coil. And we see that what we need to do in the two equations is to get rid of F, meaning to take F from one equation and put it into the other. And we see that it's not easy, because there's a cosine of F there. There's a derivative of F, so the equations are more complex. And then we can try to solve these equations in the situation where F is small. Because if F is small and we look at the electric current equation, we see that we can approximate sine of F as equal to F. And then the current is proportional to the phase of the condensate. So essentially the phase of the condensate for very small f is a direct measure of the electric current. And what does that mean? It means that this circuit with a capacitor and a Josephson junction at a small phase behaves analogously to an inductor-capacitor oscillating circuit. And this is where today's 3 Nobel Prize winners come in, because they, following Leggett's suggestions, managed to build this system and were able to show the two things. First of all, that the pairs with spin really do tunnel across the Josephson junction. And the second thing is that this system is indeed an oscillating system at small phases of the system with the capacitor and the Josephson junction. And pay attention, the most important thing is that it can be quantized. Because let's remember Tony Leggett's original idea, which said that we know that when particles are very small, their motion is quantized. That is, if we take the electron that orbits around the nucleus, classically we would have continuous energy levels, not constant, but in the quantum case we have quantized energies. And we know this from the quantization of the harmonic oscillator, the simplest quantization. That is, if we quantize that little ball and imagine that little ball as an elementary particle, as often happens in energy, inside atoms you can find such models. Then, if we quantize this motion, we won't get continuous energy levels, but we'll get a few energy levels with the distance between them given by the frequency of the oscillation. So, what did Tony Leggett say? He said this: in these electrical circuits, which are large superconductors, we can achieve a quantization of these energy levels. Well, that's what the 3 Nobel Prize laureates did. That is, they built such a system like a Johnson & Johnson, cooled it in such a way that the system would be in a superconducting state. Yes, and they created that oscillating circuit where we have a capacitor and a Johnson & Johnson. And they showed that when the system is in this superconducting state, indeed the energy levels are not continuous. Indeed, the system becomes discrete and energy levels appear where the distance between the energy levels is given by the oscillation frequency. This time, yes, of the capacitor junction system in the situation where we are still in the case, pay attention, in which the condensate phase has value.
Goodbye.
Well, as I was telling you at the beginning, Anthony Leggett was part of the committee that reviewed my doctoral thesis. He is one of the professors there. And why is that? Because I collaborated with him in the last year. In the last year, I did measurements on superconductors, and together, after several years, we even managed to publish a paper. So it's a paper with my name and Professor Leggett's name, and of course the other collaborators and my professors as well. Professor Anthony Leggett won the Nobel Prize in 2003, the same year I got my PhD. But he received it with, as I say, with greater importance due to the phenomena related to superfluidity. Although at that time it was known that he had a huge influence in this field as well, that of superconductors. Anthony Leggett is essentially the one who comes up with this idea that this junction. Josephson is a very good model for studying quantum effects. Quantum physics, which generally refers to elementary particles, to study it in macroscopic objects, meaning in these superconductors that we can see with the naked eye. One example would be quantum tunneling. What would it be? Asked Anthony Leggett and other physicists then. If such a system were actually built, such a ring, a Josephson junction, and it was shown that, indeed, when the system is cooled, the current passes through the Josephson junction. So, in other words, if we put a capacitor in parallel with a Josephson junction and build this circuit, we will have quantum tunneling through that insulating layer of the Josephson junction. This is the first element that was mentioned in the Nobel speech, namely the fact that the 3 Nobel Prize laureates showed that indeed the system works as believed. That indeed quantum tunneling takes place in these Josephson junctions and in systems that are essentially large macroscopic superconductors. The second thing that was shown was the quantization of energy levels because, as we saw, when phi is small, the current is proportional to phi. And essentially the Josephson junction functions like a coil. And then we have a classical oscillator in which we can consider that the right side is associated with the charge on the capacitor. So what does that mean? It means that we have a system in which the potential energy is given by the energy of the capacitor, and the shape of the potential energy is, as you can see here, and on the horizontal axis we have the charge. And normally, for this system to understand the quantum situation, it must have quantized energies. This is the quantization of the harmonic oscillator. So if we were to measure the energy levels in this electric circuit, where we have a capacitor and a Josephson junction, we should see discrete energy levels. Well, that's what the Nobel Prize laureates showed, that indeed in such a system these energy levels are discrete and they can be measured. In other words, the original hypothesis, in which Anthony Leggett also participated, was confirmed. That this quantization of energy levels happens not only for elementary particles as it does in atoms, where the energies of moving electrons are quantized, but it also happens in these macroscopic objects. How is this electric system essentially an electric circuit made up of a capacitor and a junction? Josephson. In fact, that's exactly what was said when the Nobel Prize was awarded, that this quantization was achieved in an electric circuit. Here we come to the last part, the connection with qubits and quantum computers. Why these Josephson junctions? Why this circuit with a capacitor and a Josephson junction? To talk about qubits, I should say a little about regular qubits, but do you know that Computers contain transistors and memory elements, which can only be in two states, 0 or 1. A qubit essentially is a quantum element, where this memory element can be, in a some state, a quantum superposition. That means they are both 0 and 1 at the same time, so we have to use a quantum system. Now, our circuit, made up of a capacitor and a Josephson junction in parallel, is essentially such a quantum system. Because that's what the three who won the Nobel Prize showed. They showed that at very low temperatures, it actually has quantized energy levels. So then, what's the idea? Well, the idea is that we can use the lowest energy level for 0 and the highest energy level for 1. And since it's a quantum system, we can bring it into a state of quantum superposition, meaning we can put that qubit as either 0 or. We'll have either the lowest energy level, the highest energy level, or a quantum superposition of both. And so we created qubits with these superconducting circuits with Josephson junctions. But there's an intrinsic problem, namely that the energy levels are equidistant. The distance between them is always the same, given by the oscillation frequency, the classical oscillation frequency. So why is this a problem? Because if we want to have a transition from 0 to 1, we need to put in energy equal to the difference between the two levels. It says we have the qubit in 0 and want to change it to 1 or a quantum superposition state. In order to move this system from the energy state 0 to the energy state 1, we will have to give it an energy that is proportional to the difference between the two levels. Looking at all the energy levels, we see they are equally spaced. What does that mean? It means that, in practice, a qubit that is at 1 can absorb that energy and go up to 2, or the one at 2 can absorb energy and go up to 3, or the other way around. Let's extract energy by moving the qubit from state 1 to state 0. And actually, let's take energy from 2 and drop it to 1. So in other words, in practice, if we build qubits with this system, even though it's quantum and allows us to have these transitions because it's a quantum level, we would have a problem. It wouldn't be very stable. With so many equally spaced energy levels, our quantum system would jump around pretty randomly, and somehow our qubits wouldn't last very long. So we had a system, let's say a worse design of this system. Well, and here's where the big advantage of Josephson comes in, because she is a nonlinear electrical circuit element. What does that mean? She doesn't behave exactly like a coil. Just like we approximated when we said we're working at Fi with the phases of the condensate at very small values, because then that phase was proportional to the current. However, normally we should go back to the two equations and not make this approximation. Let's say, okay, what is the connection between voltage and current through the phase? We'll see it's not easy since they are no longer linear equations. And if we try to express the voltage as a function of the current, we'll get a very complex formula. In other words, if we express voltage as a function of electric charge, remember how electric charge related to position for the pendulum? Yes, you no longer get a curve that is perfectly parabolic, like in a classic inductor-capacitor circuit, but instead you'll get a curve that deviates from this parabola. Well, and because of this deviation, when we quantify energy levels, we'll see that the distance between the energy levels is different. And that's what we wanted. Why did we want this thing? If the energy levels are spaced differently, sending energy through an electromagnetic pulse works. To bring the qubit that is in position 0 to position 1, it will jump to 1, and the one that's already at 1 can't jump anywhere else. Because the energy doesn't match between the energy level at 1 and a higher energy level. So, in this case, the system is very stable. Well, then what do I actually have to do? Essentially, you have to work at higher phi phases so that it's not a linear approximation, which basically means slightly higher currents. And then I'm in this nonlinear regime, where the energy levels are no longer equidistant, and then the levels. The transitions that happen at the frequency I want always occur between 0 and 1. So I only move my system between 0 and 1 because I always give it an energy through the electromagnetic pulse, which is exactly equal to the difference between the two levels and not the difference between other energy levels. Well, and this is the essence of the quantum bit based on which quantum computers are built later, using quantum bit S. Well, you realize there are also other additional elements because what we've talked about here is very, very simple. And we've seen that at some point current is also injected so that with the help of that injected current, a decision can be made, whether it's about writing, whether it's about reading the memory and so on. And in the end, of course, these reads and writes are done through electromagnetic pulses. Well, we've reached the end of this video. It's true that in the second part it took me a bit longer, also because my camera stopped in the meantime, and so I dragged out the second part. I'd like to add two things that I wrote down here. First, the word macro, and second, 2E macro. I mentioned at the beginning that this superconducting state is considered a macroscopic quantum state, because that phase of the superconducting correlate yes extends throughout the entire superconductor, so in a visible macroscopic object. To be honest, I have a deeply philosophical problem with this definition. I prefer the definition of the word macroscopic that's related to gravitational forces. In other words, an object is macroscopic. If I can feel its gravitational pull, I'm not saying if it can curve space-time, but if I can feel its gravitational force. Gravitational attraction forces have even been measured for tiny objects, like a hairpin. I think that's about where the world record is. I should check. But these are macroscopic objects. The truth is that the electrons in this correlation are very, very numerous, but their mass isn't enough for us to measure their gravitational attraction. Because then we could really talk about macroscopic objects. And then we could really try to unify quantum mechanics with Einstein's theory of relativity. Why could we go in that direction? Well, not necessarily to unite them, because we could put this correlate into a state of quantum superposition. And let's say when it's on the left or on the right, let's say yes. Then we can see if it attracts us gravitationally from the left, right, or both at once, and so on. Alright, so that's my remark regarding the use of the word macroscopic. And the second thing, 2E, meaning the electric charge, appears twice in the formula. It's normal for it to appear twice because we talked about the pairs with hair. In the Josephson junction, it's not a single electron that tunnels, but a pair of electrons, and both appear. If you look in the formulas, Planck's constant appears, and no other material constants appear. Let's say yes. Well, that means, it gets reduced. In physics, magnetic flux is considered quantized, meaning there's a fundamental unit of flux. But the basic idea is that once you've quantized this superconducting system, you're referring directly to the fundamental constants, not to material constants. And this allows you to address fundamental issues when it comes to measurement. For example, if you want to make an oscillator and you want to know exactly what that frequency is in relation to the fundamental constants, you can use these superconductors. So they are somehow like natural clocks of the universe, which bring you these conduits. They bring fundamental constants to the surface. And that was today's video. I hope you enjoyed it. I hope you take something away from it. Not just with the memory of a Nobel Prize, but with this idea that connects superconductors to qubits and quantum computers. At least maybe you'll remember how a qubit works, because Prasura explained it all to me. Yes, just a moment. We have that inductor-capacitor circuit where the coil is replaced with a Josephson junction. And that Josephson junction has a special relationship between voltage and current due to some quantum effects, right? And there it gives you a nonlinearity, and those energy levels become quantized. Two of them are very important, 0 and 1, if that's all you remember. And I'm very, very happy. I always try to make these videos under half an hour. I don't know if I managed to do that today, but I'll try in the future. Maybe I'll include fewer points and actually talk less about each one. Do you know the ending story? I'm Christian Prasura. If you haven't subscribed yet, click the subscribe button now. You can always find me on Patreon. Did you see over there? I give you private answers to your questions. And all contributions are welcome because they help this channel. No, until next time, I'm Christian Prasura. You are cool. All the best. Goodbye. Thank you.